Let's now discuss the different functions that geosynthetics can fulfill. We'll start by recognizing that there may be geosynthetics that can fulfill more than one function. In this case, we classify the different functions into primary functions and secondary functions. For example, this type of geotextile happens to be a high-strength woven geotextile that has been conceived primarily to work as reinforcement, for example, for stabilizing a steep slope. However, this woven geotextile also can provide in-plane drainage as a secondary function. Both of them are very relevant and can work together in a given geosynthetic. This brings us to the philosophy of designing by function, which is the basis of a very important book, Designing with Geosynthetics by Professor Kerner. It's a series of steps will take us to the appropriate design using geosynthetics, and it starts by evaluating the criticality of an application. Let's say that the application is reinforcement. It's going to be different to design a retaining structure that is going to serve a nuclear power plant than one that is going to serve a secondary road. Then we need to identify the functions that the geosynthetics will fulfill. Reinforcement, in-plane drainage, for example. Once we have identified the function, we need to come up with what is the required property value that is needed. This comes from design. This comes from calculation. For example, the tensile strength that is needed to satisfy stability. In addition to that, we need also to quantify what is the magnitude of the property that we have. This is the allowable property. This comes from the laboratory, from testing. What is the tensile strength that a geosynthetic can offer, for example? Now is when we're going to compare the magnitude of the property that we have with magnitude of the property that we need. And the definition of factor of safety is going to be in the numerator, the allowable or tested property that comes from the laboratory, and the denominator, the required or the calculated property that comes from design. Then we need to evaluate the factor of safety. A factor of safety of 1 means failure, but very often we're going to need factors of safety of 1.5 or 2 or maybe 3. It all depends on the type of application. After having satisfied an adequate factor of safety, that we're going to prepare specifications and eventually observe a construction and a post-construction performance. So with this general framework established, let's discuss each one of the different functions. Starting with separation, a mechanical improvement function. The idea is that geosynthetic will be placed between two dissimilar earthen materials, and this separator will keep the materials apart to maintain their integrity and functionality. A good example is that of a geotextile used to prevent that the base course of a road be contaminated with the fine-grained soils that may constitute the subgrade. Here we have an illustration in which we have a base course, the unbound aggregate of a roadway that has been contaminated with the fine-grained soils of the subgrade. For all practical purposes, a mixture of gravel and clay will behave much more like a clay than the gravel. And the gravel is the component of a roadway that provide the stiffness that we need because we are designing a roadway to minimize deformations. So here we have that this area is a transition zone of intermixed material, and over time, we have been losing the thickness of the gravel for which this road was designed. The solution is very simple. Let's place a geotextile separator. It's one of the most cost-effective geosynthetics, and by maintaining this separation between gravel and the soft subgrade, we are maintaining the integrity of the gravel. What are the key properties that we need for separation? Essentially, what we need is that the geotextile survives, exists. And there are a series of tensile properties, but they are of comparatively simple tests that will establish the ability of geotextiles to survive installation and to maintain its performance. They include tear strength, grab strength, and puncture strength. Again, index mechanical properties that will establish the survivability of the geotextile separator. Together, there is a specification that is called AASHTO M288 that quantifies what is the magnitude of these different mechanical properties to satisfy survivability operator. Just to further evaluate the mechanisms are involved in the intermixing of materials, in the case of a roadway in particular, when we have an unbound aggregated gravel in contact with a soft subgrade, there are two mechanisms that play a role in the long-term performance due to the lack of separation. One of them is when the gravel material have a localized bearing capacity failure and they are going to be punched into the underlying subgrade. An additional mechanism has to do with the presence of water. Because of the dynamic loading of the traffic, the pulses will create a pumping and the fines will go upward and contaminate the base material. So we have downward mechanisms of failure and upward contamination as well. The solution to this problem is comparatively simple. Let's place a geotextile separator between the two dissimilar materials to maintain their integrity over the design life of the structure. Let's go to the second function, which is reinforcement. In this case, we are going to ask more from the geosynthetic. We're going to ask not only to survive installation, but also to develop tensile forces. These tensile forces are intended to maintain and improve the stability of a geotechnical system. That is, we want to avoid collapse. An example is when geosynthetics are being asked to develop tensile forces to increase the margin of safety in a reinforced steep slope. This is a schematic view of a geosynthetic reinforced slope. This is a very steep slope and would not be stable without additional help. A potential failure surface could tend to develop, but having these reinforcement layers that are intermixed with the soil layers develop a tensile force that will help in maintaining stability. But not only we need adequate tensile capacity, we also need that the interaction between geosynthetic and the soil be particularly good. That is because the tensile load is transferred to the soil through shear. So what are the key properties? Well, we need to develop a tensile force. So consequently, we will need to make sure that we have adequate tensile strength. And we need to transfer the load between the soil and the reinforcement, so we will need some measure of the interface shear strength, delta. Other different way of quantifying the interface shear strength is called a pull-out resistance. We also need to make sure that we're designing the ultimate tensile strength, not for the tensile strength that we have at the time of construction, but the tensile strength that will remain at the end of the design life of the structure. Over the design life of the structure, there may be some reductions in tensile strength that need to be accounted for. This includes creep, so we will need to quantify what is called a reduction factor for creep. As a reminder, creep are time-dependent deformations. Then we may also have a decrease in tensile strength due to installation damage and chemical durability that may compromise additionally the tensile strength or the mechanical properties in general, and this can be quantified with a reduction factor for durability. I thought that it would be interesting to show you that this is not only a cartoon, but it's actually a model that was brought to failure. And here it is a full 3D version of the model, but here is the actual model. And this model was brought to failure by placing it in a geotechnical centrifuge. What is interesting is that the model failure is very much like the one that is considered in the design. The models failed because of having achieved the tensile capacity of the geosynthetic reinforcements. Ultimately, the advent of geosynthetics brought a new approach for the design of retaining walls. 40 years ago, there were two main approaches for the design of a grade separation. One was to design a concrete retaining wall. The other extreme was to design an unreinforced slope. Today, we have two additional alternatives. One is to design a reinforced wall, which essentially will provide the same vertical grade separation as a concrete gravity wall, but with a significantly better performance and lower cost. And the other is to design a steep slope that may provide advantages in relation to the unreinforced slope in terms of real estate. Here is an example of a reinforced soil slope that was constructed in the Idaho National Forest in order to widen an existing two-lane road into a four-lane road. It had to be constructed within the same right-of-way, so essentially this meant bringing a 2-to-1 slope into a 1-to-1 slope, which would have been unstable without geosynthetic reinforcement. And here we see the construction of a geotextile reinforced slope. Let's go to a third mechanical function, stiffening, also known as stabilisation function. In this case, the geosynthetic is going to develop tensile forces, but they are intended to control deformations. Consequently, it's not the tensile strength that is going to govern design, but are going to be the mechanical properties that improve the stiffness of the soil geosynthetic composite. A good example comes also from roadways, because in this case, the geosynthetic can be used to improve the mechanical properties of the unbound aggregate. It turns out that roadways are designed for serviceability. Consequently, we need to control the deflections, the deformation of the system. That's why we have a stiff base. The traffic load is transferred through the base, and eventually the load reaches the subgrade. We want this load to reach the subgrade in as wide of an area as possible, and that's in order to minimize the contact pressure. This is achieved if we have a comparatively stiff base. So if we have a geosynthetic that works for stabilization of that base, here we have this red geosynthetic at the interface between the base and the subgrade, what it will essentially do is stiffen the base, and higher stiffness means smaller contact pressure. The key properties are going to be the geosynthetic stiffness. This is measured under unconfined conditions, and this is necessary, but it's not enough. In addition, we need to transfer the load from the geosynthetic to the soil, and this is achieved by having good interaction between the soil and the geosynthetic. One measure of that interaction, we have seen the interface shear delta. There are other measures of the soil geosynthetic interaction. They can quantify the interlocking that may occur between these two materials. There is a property that combines the stiffness of the geosynthetic with the soil geosynthetic interaction in the form of a confined stiffness of the soil geosynthetic composite, or KSGC. Let me tell you a little bit more about the mechanism by which the geosynthetic will improve the mechanical properties of the unbound aggregate. Remember that a gravel or an unbound aggregate in general is a good material, but only if it has adequate confinement. A granular material without confinement will not have a good performance. But because of the dynamic loading of the traffic, we may have lateral displacements within the unbound aggregate. And this creates a domino effect. The lateral displacements will induce a loss in confinement, and the loss in confinement will create a loss in the mechanical properties, including the stiffness of the base, and the decreasing stiffness in the base will eventually lead to a concentrated stress distribution that will increase the rutting, leading to failure of the road. Instead, if we have a geosynthetic stabilized road base, we will have a geosynthetic that will maintain the integrity of the unbound aggregate by preventing or minimizing the lateral displacement that eventually will lead to a decrease in the stiffness of the base. Seeing is believing, so here we have a road lane with a geosynthetic stabilized base course. This is in a road in Texas. What I'm not showing you is this other half of the road, and here we have the two lanes, very different performance. The two lanes have the same soils, the same weather conditions, very similar traffic, the same structural package of the road. The one difference is that one lane has a geosynthetic stabilization, the other does not, and you can clearly see the difference. Let's continue with the hydraulic functions of geosynthetics, starting with filtration, which involves cross-plane flow. There are two important aspects that we need to consider in a good filter. First, we need to let the water flow through the geosynthetic easily. And second, to avoid the movement of salt particles from the retained soil along with the water. So here we have a geosynthetic, and we'll identify first that we do have adequate water flow across the plane of the geosynthetic. A good example is a geotextile being used to prevent that soils migrate along with the water into a drainage layer. What are the key properties? One is going to be what we're going to call the permittivity, which is the hydraulic conductivity of the geotextile in the normal direction divided by the thickness of the geosynthetic. The reason why we are combining the hydraulic conductivity and the thickness is that we do not want to have to establish how much of the hydraulic capacity of the geosynthetic comes from the hydraulic properties of the geosynthetic versus how much it comes from the actual thickness. So permittivity is the cross-plane hydraulic conductivity of the geosynthetic divided by the geosynthetic thickness. So here it is, the geosynthetic thickness T. Let's define also the cross-sectional area in the geosynthetic A. Because there is water flow, we will need a loss in hydraulic head. How does this work within the context of Darcy's law that governs the flow across the plane of the geosynthetic? Okay, in this case, the flow Q is going to be the hydraulic conductivity in the normal direction times the hydraulic gradient, which is in the drop in hydraulic head, divided by the thickness. The thickness in this case is the length over which the hydraulic head drops, times the cross-sectional area. Again, this is the hydraulic gradient I, and here we have the combination of the hydraulic conductivity in the normal direction with the thickness to define the permittivity. Ultimately, the flow in the cross-plane direction will be the permittivity times the hydraulic drop times the cross-sectional area. There is a second important property, and this has to do with a measure of the pore size distribution within the geosynthetic. We're going to call it the apparent opening size, AOS, or the O95. I'm going to tell you what the O95 is. So here we have a schematic of a filter, a geotextile filter, that is retaining a soil. Water needs to get through. Maybe some particles will get through, but ultimately this will become a stable filter once no additional particles move downstream. There are a number of criteria to define a good filter. I'm going to show you just for illustration a very simple one, but one of the main concepts is to compare a measure of the big pores in the geotextile with the big particles that are retained. And if the comparison is favorable, this will become a stable filter. For example, one criterion establishes that the AOS, which is the O95, is less than a certain multiplier of the D85 of the retained soil. What is the O95 and what is the D85? If we plot a grain size distribution type chart, in the vertical axis, the percentage finer that a given size, and in the horizontal axis, not the particle size, but the pore size of the filter, we will have a pore size distribution. But the O95 is the pore size such that 95% of the pores in the geosynthetic are smaller than that value. Let's say that the O95 corresponds in this cartoon to this opening in the geotextile. This is a surrogate for one of the big pores in the geotextile. We're going to compare this with a big particle in the retained soil. So if we plot the grain size versus percentage finer, the D85 is illustrated in this schematic. And let's say that the D85 in this cartoon is this one particle illustrated here. So essentially what this filter criterion tells us is that if we have the right ratio between the pore size distribution and the particle size distribution, we will have a stable filter in which the particles will be retained and the water will flow easily. The second important hydraulic function is the barrier function. In this case, we need to minimize cross-plane flow. For example, a geomembrane used as a barrier to downward migration of contaminated liquids at the base of a landfill. Here we have an illustration of, let's say, the bottom of a waste containment facility in which we have a subgrade, a drainage layer, and a geosynthetic barrier. When we consider the importance aspects of a geosynthetic barrier, this is not only the characteristics of the barrier itself, but also those of the system. For example, what is the magnitude of the head on top of the liner? Here we have illustrating the head acting on the liner. The key properties will be different for geomembranes and for GCLs. For geomembranes, it will be particularly relevant the polymer type. If it is an HDPE, high-density polyethylene, or a PVC, polyvinyl chloride, they will have different characteristics, different advantages, and different disadvantages. It will be a very important aspect in the evaluation of the long-term performance of geosynthetic barrier for a given project. An additional one will be the thickness of the geosynthetic barrier. This plays an important role not only in the long-term performance of the barrier, but also on the quality of the seam. In some cases, when we have the geomembranes in a slope, we will need to quantify the interface shear strength to satisfy stability. The one property that is not shown explicitly here is the hydraulic conductivity of the membrane. How come? Well, it turns out that the hydraulic conductivity of the membrane is so small that for all practical purposes, if the geomembrane is intact, then the flow through the geomembrane will be essentially negligible. But that's an important if the geomembrane is intact. So much of the design of the geomembrane will be how to minimize potential defects during installation and the operation of the barrier system. The other important geosynthetic barrier is the GCL, Geosynthetic Clay Liner. In this case, yes, and we should quantify the hydraulic conductivity of the bentonite, and because the interface shear strength and the internal shear strength of the bentonite is so low, we will need to quantify it and account for it accordingly. Here we have an illustration of a GCL being placed in a waste containment facility. It's notable how easy it is to install a roll of GCL. Essentially, the task is to unroll a roll. Compare this with a significant effort of placing, moisture conditioning, compacting a compacted clay liner that potentially will have a similar performance as this GCL. And here is a very scenic picture of a geomembrane protecting filtration against the mining waste in a mining site. Geosynthetic barriers are used not only in geoenvironmental applications, but also in hydraulic applications. And here we see a lined earth dam with a geomembrane placed on the face of the dam before placing a riprap. There's no geosynthetic in this picture, but the reason that I'm showing it is to illustrate that concrete dam may leak. This is relevant because typically when we think of a material that is very durable, we think of concrete. And indeed, this clearly shows that that's not necessarily always the case. In fact, many concrete dams in the US were built in the 1960s, and now when many of those concrete dams are being retrofitted, like the one that we show in this picture. And what is the technique that we use to retrofit the dams is by lining them using geomembranes. The third hydraulic function of geosynthetics is drainage. And by drainage, we really mean in-plane drainage. That is when the geosynthetic allows the flow of liquid within the plane of the geosynthetic. So here we have a view of the geosynthetic and a flow queue within the plane of the product. An example is a geocomposite drainage layer used to convey liquids in a waste containment facility. Key property is the transmissivity. Also in this case, we will want to combine the relevant hydraulic conductivity with a thickness. In this case, it will be a different combination because the thickness plays a different role than in the case of the cross-plane flow. The transmissivity is Kp, the in-plane hydraulic conductivity of the geosynthetic, times the thickness of the geosynthetic. Here we have in this sketch the different geometric characteristics of the geocomposite drain, a width W, a thickness T. Because there is flow along the geosynthetic, we will have a drop in head. So let's say that we have two piezometers with a distance delta L and a drop in head delta H. So how do we invoke the good old Darcy's law in this particular case? Well, the flow will be the hydraulic conductivity in plane times the hydraulic gradient, which is delta H over delta L, times the cross-sectional area. And it's important to notice that the thickness is part of the cross-sectional area in this flow problem. So that's why when we combine the in-plane hydraulic conductivity with the thickness, this will be multiplying these two variables. Ultimately, the flow in plane will be the transmissivity of the geosynthetic times the hydraulic gradient times the width of the product. This is a view of the installation of a geocomposite drainage layer to illustrate how simple it is to place a geocomposite drain. Compare this with the effort that it would mean to transport, to place, to compact an equivalent granular drainage layer that would be somewhere in the order of 30 centimeters. And the final function that we're going to discuss is the protection function, in which the geosynthetic is used to limit local damage of perhaps another geosynthetic, for example, a geomembrane. And that is the example that we have in here, a geomembrane that is in contact with a gravel. We need to protect the geomembrane against the direct contact with the gravel. This is typically done with a geotextile that serves as a cushion, as a protection placed between the gravel and the geomembrane. Here we have a three-dimensional scanning of an actual gravel particle acting directly against a geomembrane, and we can see the imprint and failure due to puncture of the geomembrane. Key properties are going to be the puncture strength of the protection layer, in this typically a geotextile, and its thickness. An example in a waste containment facility, here we have a compacted clay liner, on top of which we have a geomembrane, and on top of the geomembrane, we need a drainage layer, in this case a gravel. But in order to protect the geomembrane from the gravel, we have a non-woven geotextile. Here's a cartoon to illustrate better what we see in this picture. We have a compacted clay liner. On top of that, we do have a geomembrane. On top of this, we have the non-woven geotextile that is serving as a protection layer, then the gravel, which is the drainage layer for the system. Also, as protection layer, we include erosion control. In this case, we consider this being protection because it's a protection of the surface of a soil slope against rainfall. For example, a permanent geosynthetic mat, call it as well a geomat, placed over an exposed soil surface. And here we see a combination of the geomat and vegetation providing erosion resistance. Other forms of erosion control can also involve geosynthetics. In the middle picture is an example of a sealed fence that typically involves the use of geotextiles. And in the picture on the right is a more robust type of erosion protection, in this case involving geocells, protecting the side slope next to a roadway. And this is a time lapse showing soil erosion by surface water, just to illustrate the significance of inappropriate erosion control. As an example, here we see the use of an erosion control mat placed on a reinforced soil slope, the one that I showed to illustrate the reinforcement function, in this case shown to illustrate the use of erosion control for an exposed slope. Eventually, this slope was vegetated, and vegetation along with mat contributed to erosion control. So in summary, we have completed the description of the different functions of geosynthetics, including the different mechanical functions, separation, reinforcement, and stiffening, as well as the hydraulic functions, in-plane drainage, filtration, and hydraulic barrier, and finally, protection that also includes erosion control.